Happy 105. Welcome back to the final installment of this summer's Neuron Online course. Thank you so much for attending. Do be on the lookout for a survey from us later for any sort of feedback that you may have. Ted, do you have any introductory things? Otherwise, I have a little bit of, I want to talk very briefly about the HOC exercise from last time. And then I think it's up to you for initialization or whatever else.
Sure, that's fine. I do want to say one thing. We really appreciate the questions that people have asked and the discussions that have ensued. Even questions that seemed a bit off the mark at times, because it brings fresh material in and connectedness to other related research. So go ahead, Robert.
Oh, also, I guess I should point out, so there's a couple of examples that were posted to the Ask Tutors channel on Sunday, where there was a Colab notebook used for storing arbitrary data at spike times. You may want to check that out if you haven't looked at that. And there was also a Colab example of using a current clamp for non-constant stimulus. So suppose that you wanted to do a ramp stimulus, for example. So there's an example on Google Colab of that as well on the Ask Tutors channel. So these may be of interest to you.
Well, very briefly about that, did you use vector play with interpolation, or did you use a fully filled in vector?
Vector play with interpolation. And so to get a discontinuity, you have to say the same point twice.
Great. Yeah, that's the really efficient way, because you can handle some fairly complex waveforms with just a few breakpoints.
Absolutely. I think, yeah, because if you do a lot of points, I guess with a variable time step, it's going to be very unhappy if you oversample the time.
Not to mention, it's easy to make mistakes, you know, when you're setting it up, so.
All right. So just very briefly, so last time I had asked you to take a look at this HOC exercise, which hopefully you're seeing. It was a code that did something that we hadn't actually done before. We haven't done in the course. We're not going to do in the course. It builds an interface. It does a thing. Did anybody play around with this? Did you look at it? Did you figure out what to do? Did you figure out, did this give you enough insight that you could figure out how to go, since you can read HOC now, how to go and actually do something similar in Python? So like this is a silly toy example, but you could easily hook this up to Hodgkin-Huxley or whatever simulation you're doing. Okay, so let's suppose hearing nothing. Let's suppose that you came across something like this in your you came across something like this from your lab's code repository, from some historical example back you know, however long ago, and you don't want to use this. I mean, if you just want to use this, you know, you can just do an h.load file and it'll do the things. We do this all the time with the standard run control, with import 3D, h.load file is great for that. But you can do this with your own labs functions and stuff like that as well. But if you come across a thing and you're like, how does this work? I see there's stuff about buttons. How does this work? You want to actually think about this. My advice in general, anytime that you come across some code, as long as you're reasonably sure that you can trust the code, don't do this on, you know, if you don't trust the code, you don't trust the source. But if you come across the code, you trust it, there's nothing nefarious going on. You want to figure out what it does and how it does it and how you can adapt it for your own purposes. the one way to really truly know what something does is to try to run it, and at least you can figure that out. And then if that works and it does something interesting, you could try breaking it down to pieces, but this one's, I think, fairly straightforward. So maybe you don't need to break this particular one down to pieces. But what I would say, my advice to you is if I come across a thing that looks interesting. All right, here it is. I've got this HOC file. It looks interesting. I'm just going to say enter in GUI exercise.hoc. And then that's going to pop up. That did some stuff on the other screen here. It's going to pop up the Neuron main menu because I ran enter in GUI. It's going to run whatever my HOC file is. So exercise.hoc, the code here. And now I can start to map and to get a sense as to, okay, well, the big thing that it did is it popped up this window. What could be causing this window? Well, I see it's got the word menu. I see it's got some text, a field, and some buttons. Well, okay. We've never talked about how to do interfaces in Neuron. We know Neuron supports it, but I can sort of map and I can say, oh, well, there's a thing that says menu. Maybe that has to do with this thing that says menu. There's a thing that says pick parameters in a simulation. Okay, that seems like it's this part. Okay, and blah, blah, blah. And I can get a sense. And if I were to hit these buttons, there's no point of having a button if you don't press it, right? So let's press it. Do count. It counts from 0 to 4 inclusive. Do half count. It counts from 0 to 4.5, but now by a half. And then so you say to yourself, well, self, can I understand why it is that it's storing this? Well, you're like, I think so, because it looks like when I press the do count, it's counting by 1. I see a thing that says t equals t plus 1. Maybe this is it. How do I know? How do I test if I've understood this correctly? And I would suggest, you think you know, and this is true, by the way, this is true for HOC or Python. This is true if you come across something on Stack Overflow, wherever it is. You think you know what's going on. Do the experiment. Modify it. See if the changes that you think would happen actually do what you think would happen. So if I were to quit this, and now I were to say, I think that line that says menu is why it said menu in the title bar. So let's put something else here. This is button picker test. I don't know. If I change the text and I run it, do I get the expected results? And I do. So that line clearly corresponds to whatever goes here. And I can start to map this out and I can start to think things through. I'm like, okay, figure out what's going on. Even though it's new code, even though I don't fully understand it, I can start to make modifications, see how the modifications affect the behavior. Sometimes it's good to go backwards to make sure, you you make a change or a series of changes. It seems to to change in one way. It's always nice to go back and see if you can restore the original functionality to see if you truly understood what it was that you did that caused it to behave differently. But so this is a sense of how you can explore all of this. My suggestion to you, though, so we can do all of this and we can kind of look at this, and clearly pressing do count is calling this do count function. And then you can see it's a for loop. It starts at 0, goes up to t-stop, counting by 1. There's a half count, starts at 0, goes up to t-stop, counting by a half. And if I change this, does it do what I think it does? So if I change this to only go up to 2, and I say do count, goes 0, 1, do half count, 0, 1 half, 1, 1.5. Cool. So we can sort of say, we say, okay, we know what this is doing. The other thing that I'd ask you to consider, though, and again, if it's a HOC file, you don't generally need to do this. But if you're just reusing something, but you could imagine, can I learn a lesson here about how to do the same thing in Python? And you know certain principles, right? I mean, well, you certainly know how to do the counting in Python. All right, so those functions or procedures, I guess, in the HOC parlance, those procedures have a clear mapping to Python. What about the panel? What about all of these function calls, the calls into Neuron? What's the number one difference? What's the most obvious difference between calling Neuron things from Python and calling Neuron things from HOC?
H.
H. Okay. So let's see. Can I do this real quick here? Let's make a new window. Let's go ahead and I will, here's a new thing. I will just do this in Python. Well, I know I want to do a graphical thing, so I'll do from Neuron import H and GUI. If you need the graphical interface, always import the GUI. Okay, so I have an X panel. So how do I do X panel? Well, it's a Neuron function, and HOC is just X panel. So in Python, it's probably H.X panel. And so you could imagine that I've got all of these calls to Neuron. You could imagine that you start out, well, let's just say H.X panel, H.X label, H.X p-value, H.X button, H.X button, H.X panel. All right, that's going to get you much of the way. It's going to yell at you, though. There's a Python syntax error here. So let's just save this. I'm just going to save this in the same folder, even though it's not when I actually did it. So this is exercise.py now. Uh-oh, I got some red squiggle lines. Why do I have red squiggle lines on this?
Ampersand stop.
Ampersand t-stop. Oh, that's not Python. But what does ampersand mean in HOC?
It's a reference, right?
What's this?
Reference.
It's a reference. So I need a thing that I'm going to take a reference to. So in order to create a reference, so I can't use literal pointers in Python. Python goes out of its way to make sure you don't mess directly with pointers, but I can create a reference to a thing, and I will call my, I will do that by using h.ref to create a reference to a thing, and the reference value that I want to do is going to be 5. And now, since it's already a reference, I'll just pass in t-stop. And now, at least all of my red squiggles have gone away. That's always a good sign. I haven't done anything clever about the functions. That's probably going to be a problem. But let's see what we have. All right, so now, if I type this, well, actually, let me just go ahead and do this wrong first. If I just type Python exercise.py, I'm going to be disappointed. Can somebody tell me A, why I'm going to be disappointed, and B, how to fix it? What's our hypothesis? What's this going to do?
You are calling something which is not defined.
Well, only if I press a button. If I don't press a button, I'm not calling something that's not defined. I mean, you're right. You're right. That's going to be a problem, but there's a problem before. And yeah, so there's two. Yeah, sorry, go ahead. So there's two people who said the right answer on the chat here. But so just to really drive this home, if I just run this Python exercise.py, it immediately terminates. Why? Because it doesn't know that it needs to wait for me. So as Ben and Salvador both point out on the chat, the correct solution is to run this with a -i flag saying that I want to run this interactively. Now, when I do that, it pops it up. This shows up on my other screen. Sorry about that. But sure enough, I have all of these things, and t-stop has the value that I expect it to. All right. So I've now gone, even though we never talked about how to do interfaces in Python, I took my HOC example. I now at least have some basic interface happening in Python. That's pretty cool for not a lot of effort. Now it's been observed, and you're correct, that if I were to hit do count, well, right now it's trying to call something that isn't defined. And it's going to yell at me, and we're going to be sad. But that's okay. We didn't define it. So remember, let's look at this. So in HOC, the HOC doesn't have functions as first level objects. So in HOC, every place, you have all these places where you can take strings of HOC things to do. And the analog, though, in the Python world is just to put the function there. Because Python's perfectly happy working with functions. So let's define two functions, a do count and a do half count. And we don't even need to translate these. We can just sort of think through. So here's our functions. Define do count. It's not going to take any arguments. It's going to count it. It's going to start at 0. Let's say t equals 0 while t is less than t stop. Comment on that in a moment. We'll print out the equivalent is t equals t, obviously with the curly braces and an f string, and then t plus equals 1, t equals t plus 1. I can't type apparently today, or we could be even more clever and just use a regular for loop and a range. I know that, you know that, but this is sort of most directly analogous. There's one problem though. What's wrong with this function? Why won't this function work? What's t-stop? T-stop is a reference. How do I go from a reference to the reference's value? We've done this all the time, right? We have a pointer. If I have h dot underbar ref underbar t.
Underscore ref underscore.
Well, no, but that's how we get a reference if we have a neuron object. But if I have h dot underbar ref underbar t, how do I go from that to the actual value of time? Like let's say Python from neuron import age. All right, now I'll say that h dot t is 47. And then here's my ref. My ref is h dot underscore ref underscore t. But how do I go from that reference object? That's a thing that points to the value of t, which I already have, right? I'm calling it t stop here in this other code. That's a pointer to the scale at 47. How do I go from that to the number 47? What I want is ref plus 1, right? I want to get 48. How do I go from that pointer to the value? How do I dereference it? So this is a carryover, incidentally, from, so in C, there's two ways to dereference a pointer. One, there's a whole special asterisk operator for that. We don't have that. We don't need that. The other way is a pointer is the same thing as marking the beginning of an array. And then so you do square bracket 0 to get the thing that's 0 offset from that memory location. So if I have reference and I do square bracket 0, it's 47. Equivalently, if I have reference of 0 and I set it to 3, I'm setting a value on that pointer. So now if I look at h dot t will be 3. So we can use square bracket 0 anytime that we have a reference, and this works in C and C++ as well, although there's other ways of doing it in those languages. Anytime I have a reference, square bracket 0 gives me the actual value. So I can't, while t is less than t stop, true, but I can do while t is less than t stop square bracket 0. All right, and so the other thing that we said is that now this isn't a string because this is Python. We just straight up pass in the function, which is do count. And that's sort of a general rule. Anytime in HOC that you see a string that's a HOC command, the equivalent in Python is just pass in the function directly. So let's see if this works. Python-i exercise.py. There it is. It popped up in my other window again, whatever. Here it is. I say do count, counts from 0 to 4. I changed TSOP to be 47, and I hit do count, and it counts from 0 to 46. So we've got this. For the sake of completion, let's just finish this. We want to do the exact same thing except for half count. We'll just copy paste this sucker, and t equals t plus a half. And then we'll fix that to half count. And then this should be good. Let's find out. Now, if I run it, here we are. I hit do count. It counts from 0 to 4. I hit do half count. It counts from 0 to 4.5. All right. So what I hope you see is, first of all, there is a clear analogy between the two different languages. Obviously, if I was writing this in Python, I'd write these do count from scratch. I'd write these do count, do half count functions differently, but whatever. But there's a clear analogy on the neuron side. Functions, calls, and in HOC are just strings of HOC commands. In Python, we just pass in the function. Anytime we need a pointer to something, we just create a ref in Python, and then we work with that ref, and then we dereference the ref if we need to with the square bracket 0. And the nice thing is we can do these experiments. We can find things that work. We can modify them. We can tweak them and try to make sense of how it is that the HOC code did a thing, and then we can modify the HOC code to do new things, or we can use that to help with Python. So it's really convenient to be able to know just enough syntax, that you can go in and start doing experiments and start trying to learn from some of these old things. Again, fundamentally, I do want to stress, if you do have a thing in your lab that's written in HOC, there's nothing wrong with just continuing to use it as long as you're not needing to make changes.
Okay,
yeah,
two questions for you. First of all, it's also good, you can use these same old methods to create simple interfaces. So, for example, suppose a newbie is coming to the lab and there's some piece of software that everybody's been using and is quite expert with, but the newbie needs a little extra help. So you can quickly throw together a user interface that this person might find easy to work with so that they don't break stuff. And you don't have to have specialized modules. I mean, there's marvelous GUI interface libraries for use with Python, but using them with any degree of expertise can be somewhat difficult and a topic into itself. So don't be hindered about using those. But if you need something fast, a quick and dirty result that actually works, this is a good way to go.
But
I do have one question. Go ahead.
Sorry, can I just make one minor comment? But just to be abundantly clear, if you do happen to know these things, and there are people out there, you might be one of them, that do know Qt or WX or something like that, obviously, all of that stuff, if you know how to do it, that's awesome. Use it. You can embed. So we've shown you doing shape plots and range var plots, which are really the only two neuron-specific graphs. We've shown you that you can do these in Matplotlib and Plotly. And so you can embed all of this stuff inside of Qt, inside of WX. So you can build an entire neuron interface into these things if that's what you want to do. However, I am going to caution you, especially depending on, you got to think about what your time is worth. And if you can whip something up in like 5 minutes, your advisor is probably going to be much happier with that, especially if it's a standalone lab experiment, than something which you spent a week working on, even if it looks prettier. So pros and cons. If you're trying to reach a large audience, and so Ted and I have certainly collaborated on tools that use Qt, it depends really on what your audience is.
Indeed. And yeah, now question for you. Suppose you had a procedure that required arguments. What would your X button argument be
That
for
is a, okay, so let's do it. So let's suppose, and actually this is a clever way of speeding things up. So really, we'd probably want, if we were being clever, well, these functions are almost identical. I shouldn't have two functions for that. Let's have a function that takes a step. And I'll just add in the step function, add in the step amount. And then I can do this with just one function. Uh-oh. But as Ted says, I need an argument now. And so the way that we do this is instead of passing in the function, we pass in a tuple, that is the function, and the arguments. So this is going to be do count of 1, and this is going to be do count of, let's actually, here's another pro tip for you. If you are making a change, and you want to make sure that you actually successfully made a change, make a visible change. You know, so that I want to know, did this work, and make sure that I saved it, and make sure that I'm running the right version. Well, now I'm going to run the quarter count version instead of the half count version, just to make sure that I'm actually running the code that I think I am instead of an old version that did work. So I quit it, I'll restart it. And again, if I hadn't quit it and restarted, I'd still have that old screen up, and I think it worked. Right? So let's find out. So here we are. Do count works. Do quarter count works. All right. So the punchline is anytime that you want to send an argument, instead of calling just the function, you pass in a tuple, which is the function, and then however many arguments. And that could be one argument, that could be many arguments. There are other ways of doing this. Python allows a thing called lambdas. If you know about them, that's cool, good for you. And also partial functions. That's another Python context. But for Neuron, anytime that you can take a function, you can also take these tuples.
And the reusability of your code depends on, to some extent, on the ability of naive users to read it and make sense out of it. And unfortunately, or perhaps fortunately, most of the people who are developing code in labs around the world are not professional programmers, and for some it's their first real programming project. So if you write some really beautiful, sophisticated, highly Pythonic thing, they're going to look at it and say, I have no idea what's going on here. And that may affect reusability. So readable, understandable code, inelegant as it might seem, might be the way to go for these kinds of applications. Save the fancy stuff for when Google hires you.
Well, I'm not sure if you count this as pretty or not, but I personally like this because this is pairing the two things together, right? Do count and the how much are in one thing, and there's no duplication, right? Like
no, this is very readable. This is completely understandable, and fine. I think this is great, and I think it's just an example that people could readily follow. The people who need it the most probably aren't the ones who are here today. Maybe they'll see the video later.
Did you have a second question on this? Anybody else have a question? Ted?
Nope. Looks good to me.
All right. Well, then that is what I wanted to say about the HOC exercises. So with that, take it away, Ted.
Here we go. We're off to the races. I'm going to be talking about something that seems to be an odd for a closing presentation, but we've been putting it off and putting it off and putting it off, and finally we have enough under our belts now to approach it in all of its complexity, and that is the topic of initialization. And very specifically, what I'm going to be talking about is the importance of being able to get and how we get the same result every time we run a simulation. This is important, of course, for us being able to debug programs. If you've deliberately built in something, God forbid, that causes you to get a completely different result every time you run it, you're going to have a heck of a time debugging that. You're going to have a hard time knowing if it works properly even. So start by developing programs that will produce the same result every time. And in particular, in our context, every time you run a simulation. So no matter whether you run it by clicking on the init and run button, or you're dealing with a distributed parallelized model of a network, and you're running psolve, parallel context psolve, you want to be able to get the same result every time you do that, no matter what you've done before. So even in the same session, if possible, without exiting Neuron. So that being the ideal, the question is, what actually should be going on? What actually does go on when we initialize a model? Well, we're dealing with initial value problems, actually, aren't we? I mean, we're dealing with sets of algebraic and differential equations, and the differential equations are not boundary value problems. They are initial value problems. That is to say, we have the values of states at time t equals 0, and we want to see what happens to our bag of equations and states going forward as time advances. So what are the things that have to be set at t equals 0? Well, obviously, membrane potential has to be set everywhere in the model. Let me see here. Mouse. Oh, well, okay. Spotlight. Yes, there we go. Yeah, so there's membrane potential is one of the big things, of course. Gating states, channel gating states, absolutely. Ionic concentrations have to be assigned their appropriate starting values. I'm not going to say much about that. That's a special topic of its own. We could spend an entire hour on that alone. Chemical reaction states in these kinetic schemes, for example, or if you have, say, for channel gating, or let's say you have a mechanism of involving calcium, second messenger triggered calcium release from intercellular stores, or let's say you have a model that involves phosphorylation of channel proteins that actually changes their dynamics. So all these things have to be initialized. And if we're dealing with models that involve linear circuits, which I don't think we've talked about really much at all, have we? You need to make sure that the charge on those capacitors in the circuits have been properly initialized. And if there's operational amplifiers that may have some kind of internal states, maybe inductors that have initial currents in them, random number generators, all of these things have to be initialized. I'm not going to talk about initializing random number generators particularly because Robert's already discussed that with regards to random 1, 2, 3. And you should go back and review that sometime, especially if you're dealing with models that involve stochasticity. All of these things so far pretty much have to do with our conceptual models and the biophysics and anatomy that's in them. But there are other things that are going on that are not part of our conceptual models, but we use them when we run simulations. And these have to be properly configured at initialization as well. For example, event queues. What do I mean event queues? Well, let's say you have designed an an experimental protocol in which you're going to have certain events delivered at certain times. Well, you want to make, then these events arrivals are going to trigger certain changes in your model, maybe changes in rate constants, maybe changes in concentrations of transmitters or some other some second messengers or something. You want to make sure that if you have set up an event queue, or if you've got a pre-recorded event queue like spike times, you want to make sure that those are properly configured. And if there's pointers to the events in those queues that get advanced every time a new event is sent, that those pointers are at the right locations in those queues. Vector record and play. Vector record and play involve counters or pointers to what's the next location to which, say, a particular recorded membrane current is going to be stored, or what's the next location that holds the value of a pre-recorded synaptic conductance that we want to play into our model, maybe from an empirical recording, experimental recording. And counters. Maybe you're keeping track of the number of spikes. Maybe you're running a simulation where the aim is to calculate, say, the average firing frequency. And you want to make sure that you avoid any initial transients while the cell is settling into its steady firing pattern. So you want to make sure that you wait at least a certain number of spikes before you start saying, okay, let's keep track of our spike times past this point. Okay, or maybe you want to run a simulation involving a learning rule, and you want to make sure that your synaptic mechanism that you're testing its new learning rule has received enough inputs. So you want to keep track of how many inputs has it been the target of. And if your synaptic mechanism is embedded inside a network model and is going to be the target not of events that you've pre-decided what they're going to be and when they're going to be, but they're going to be whenever the network model fires its spikes, then you need counters to keep track of that. Has my synapse received 10,000 inputs yet? Okay, so all of these things have to be properly set up. Well, let's take an example. Let's take a look at what finitialize itself is doing, because finitialize does an awful lot of these things. Obviously, it sets t to 0. It clears the event queue. And why is this important? Let's say you have a network model and you have cells that have that are connected to presynaptic cells connected to synaptic targets by netcons that are associated with very long delays. And your presynaptic cells have fired spikes, and there may be 100 spike events in the spike event queue at the end of one simulation. Before you run another simulation that starts at t equals 0, you got to flush that event queue. Well, finitialize takes care of that for you. Obviously, if there's any changes in topology or geometry, those have to be properly set up and reckoned, and the data structures that Neuron uses to advance the simulation from one time step to the next has to have, those data structures have to have the proper contents that depend on topology and geometry, and biophysics for that matter. The vector play controller, which keeps track of where are we in the vectors that we want to play, that we want to use as forcing functions. Delivering events whose delivery time is 0. Yeah, there are times when you want to have an event that is delivered at time t equals 0. What about initializing membrane potential? Well, one way to initialize membrane potential is to make membrane potential in all compartments set equal to some value called v_init. So if finitialize is called with a numerical argument, that numerical argument becomes the time at t equals 0 for all of your compartments. And that will be the potential to which all of your voltage-gated mechanisms will be initialized. All of their gating states will be initialized to the steady state value for that potential. Furthermore, finitialize causes every initial block and every inserted mechanism in every segment to be called. And it sets extracellulars Vx to 0, which you may not be using that, but if you were, it would. And just like the Ronco Vegematic, this F-initialize does a heck of a lot more, including initializing ions and calculating equilibrium constants, initializing mechanisms that write ion concentrations, etc., linear mechanism states, initial blocks inside net receive blocks. We didn't dwell on that, but a net receive block can have an initial block, and that initial block in the net receive block will be called at the time that the mechanism is initialized. And if that produces network events, any of those that have a delay equals 0 have to be sent to delivered to their target net receive blocks. Okay, so a lot of this now has to do with these last three things have to do with which integration method you're using. And and vector record. I just was working with a model entry in ModelDB the other day, and it worked, and it works fine, and it runs one simulation just fine. But the authors of it did a very strange thing to capture the time courses of membrane potentials. They literally executed append statements for every compartment in the model to record the local membrane potential in the course of the simulation. They didn't do vector record. Why didn't they do vector record? Well, I'm not sure. But if you tried to initialize their model to steady state using one of the methods that I'm going to show you later today, their code wouldn't work because it would capture times at negative time values to your recorded vectors. And we'll see exactly what I mean by that later on. Okay, so F-initialize takes care of properly initializing vector recordings. Okay, no discussion of initialization in Neuron would be complete without mentioning the standard run library. Neuron's standard run library contains a fairly complete and well-debugged and well-designed simulation flow control system. And when you click on init or init and run in the run control panel, or if you enter a new value for via init in the run control panel, standard init will be called. Okay, so what does it do? Well, it calls these 5 things. One of them has to do with proper updating of graphs when you're running with adaptive integration. One of them has to do with a rather primitive way of keeping track of how long simulations are running. One of them has to do with reconciling the fixed time step parameter dt with the points per millisecond parameter, otherwise known as steps per millisecond, because those have to agree with each other. So if you're saying that we're going to plot 10 points per millisecond, dt better be either 0.1 millisecond or some whole number fraction of 1/10 of a millisecond, okay? And Neuron makes sure that this happens by adjusting dt. If it finds out that dt isn't compatible with points plotted per millisecond, it forces dt to be changed. You may or may not have noticed that when you use the graphical interface, but that's why that happens. Then there's this magic thing, init, and we're going to look at that next. This next thing has obviously to do with initializing plots that are going to be updated during the run. But let's look at this init procedure. What does that look like? Why is it important? Why are we even looking at it? Before the F-initialize handler class was added to Neuron, proc init was used for most customizations. And the way people would do this is, well, proc init merely called F-initialize with a numerical argument via net. And what people would do would be to embed statements that did stuff, okay, special things, and they would put them in here, okay? And then and you'll see that occasionally when you're working with legacy code. So part of our, HOC literacy campaign, we want to make sure that when you look at that, you don't just go, what? Okay, you'll have a sense of what people were trying to do. And maybe if you're lucky, they'll even have a comment that says. But if it changed if whatever they did with these extra statements following F initialize, if it changed any state or parameter, then these statements should be uncommented. They should be used to make sure that the adaptive integrator is initialized or that currents are properly initialized and that vector recording is properly initialized, okay? Otherwise, you'll get some garbage results at the beginning of your simulations. So now you know something more about legacy code. All right, let's take a look at other things that we're going to be working with all the time. Initial blocks in NModel. As we said, finitialize executes these initial blocks. So for example, in many cases, in voltage-gated mechanisms for ion channels, you'll see that there's a initial block that starts with a call to a function or a call to a procedure, after which there follow some assignment statements to state variables typically. And so here we have a state variable m which is being assigned its steady state value at whatever the initial membrane potential is. And this is how it's being calculated in this rates procedure, which calculates the value of the steady state value of minf. And minf would probably appear in an assigned block. It would be probably declared in an assigned block in this NModel code. And this is your typical formula for calculating the steady state value of M at a voltage V. Okay? What about kinetic schemes? How are kinetic schemes initialized? Well, kinetic schemes are initialized in a different way. You'll see here's the scheme. You don't see any minf or mtaus or any other nonsense like that. You see instead forward and reverse rate constants for these transitions between the two closed states and between one of the closed states and an open state. So we have this transition with these forward and backward rate constants, and this transition with these forward and backward rate constants, okay? And we see our breakpoint block where we see the calculation of the potassium current as the product of the channel density times this O variable, whose value ranges from 0 to 1, which represents the fraction of these channels that is open. If O has a value of 0, then all the channels are closed. If O has a value of 1, then 100% of the channels are open. And there's our driving force, okay? So far, so good. We understand maybe how things are advanced from time step to time step. But what about initialization? Well, initialization calls this method steady state. It tells neuron to use the equations that it gets by translating these statements, use these equations to calculate the steady state variables for the state variables. Okay, so the steady state method is used to calculate the steady state values of state variables in a kinetic scheme. So all you basically do is you're taking the solve statement out of the breakpoint block, okay, copying it, pasting it into the initial block, and replacing the word sparse, which is the method that's used in the breakpoint block to advance from time step to time step for a kinetic scheme. You're replacing that keyword sparse with the keyword steady state. Couldn't be easier. Okay? All right. How do we initialize states generally speaking? Okay? Well, oftentimes by declaring a parameter. If you know that there's a particular value, you have a state with a name state, lowercase state. Perhaps I should use a different name for this example. what you do is in the parameter block, you declare state 0 as a new variable name, and you assign whatever initial value you want to that. And that parameter, state 0, will have that value throughout the entire simulation, and automatically the variable called state will be given that value at t equals 0. Now, I don't know about you, but I don't like to count on things as being automatic. So if I did that, I would sure as heck have an initial block in my mod file where I actually literally went ahead and did the assignment myself. Okay? So if I even remembered that this would automatically initialize the value of the quote state to state 0 value here, I just want to make that explicit because I may know this, but nobody else is going to know this. And you didn't know this until right now anyway, and you'll forget it by next week. Okay, so I like to be very explicit. I declare if I have particular initialization variables that I want to use in an end model specified mechanism, I will make them accessible from HOC and Python, because no matter what my preferred values are for these this week, next month I may decide, really, I just don't want those values. I want different values. And I don't want to have to rewrite my end model code and recompile it. I just want to pass it in as an argument. Okay? Or, just as specified as an attribute to the mechanism. So I'm going to declare them in the neuron block, and I'll declare them as either global or range. I'm not going to count on parameters as being automatically global because I know that, but how many novices know that? Okay? And, just declare it as global. And declare it as range if you want it to be range instead. And then go ahead and explicitly give it a value in the parameter block and explicitly make the assignment in the initial block. I have occasionally seen mechanisms that use this old alternative syntax where in the state block you have this statement called start, a start statement where you say state start 1. And all I can say about this is it's like what are they? Well, no, I'm not going to say it, but it's basically, it's not useful because it's obscure, and frankly, it's a wart. And it's a wart that was created because NModel was a model specification, is based on a model specification language that was created by a committee. And when a committee designs something, instead of getting a horse, you get a camel, okay? And so this is kind of like the camel of NModel, one of NModel's many camels. So I kind of avoid that, and I like everything to be human readable and very clear and explicit. Okay, but at least you'll know that you've seen this before, and you may remember what it means now that you've seen it. All right, now let's go on to custom initializations. What kinds of custom initializations do people typically do? A very common one is initialization of a model to steady state. Why? Why do you want to initialize a model to steady state? Well, for one thing, there's no guarantee that the values that will be picked up accidentally by your code are anything like what you really want. Okay? No guarantee whatsoever. So it's always best to do something with your mechanisms, and initializing to steady state is a good way to do it, because in the world of wet lab experimentation, what do experimentalists do? They like to start out with things in the steady state. When you say, when you prepare a brain slice, let's say you're going to be working on particular pyramidal neurons in a brain slice, first thing you do is you anesthetize the animal, you take out the brain, you chop it, into slices. You put the slices in an oxygenated ringer bath. You let them sit there for a while. You're letting things settle down. You're letting things tend to approach the steady state. Then you pick up one of the slices on a light brush, very fine sable brush perhaps, and you transfer it to your recording chamber where it's going to be perfused by oxygenated ringer at maybe body temperature. And you let it sit there for a while to equilibrate, typically 15 to 20 to 30 minutes, something like that. Then when it comes time to actually start poking around with either a sharp electrode or patch electrode, if you get attached to a cell or you've impaled a cell with a sharp electrode, you don't start recording immediately. You let it sit for a while because you want the cell to recover from the trauma of being patched or impaled. And also you want to know that it's going to last long enough for you to do whatever your experimental manipulations are. So you wait for a while for things to settle down. And if membrane potential is changing in front of your eyes spontaneously, you do not want that to be used for your experiment. So steady state initialization is kind of like what biologists do anyway in real experiments, where they're looking at what is kind of an unperturbed system, or at least it hasn't been perturbed very recently. Or you're looking at a system that has been subjected to a constant voltage clamp to a particular potential, or current clamp with a particular injected current. So you want that model to settle down under those conditions, under conditions of being subjected to a particular holding voltage or a particular steady state injected current. That's your steady state initialization. And you do it, these things are done in the experimental world by wet lab experimentalists, and we can also do them in our computational models. Another type of initialization is to initialize a model so that its states put it on a defined starting point on a trajectory in state space, okay? So that every last one of its state variables is specified at the very beginning of your simulation. And this is particularly useful when you're dealing with oscillating or chaotic systems that are spontaneously active. Because when you first start solving the equations that describe a model that has a, like a limit cycle, a stable limit cycle, or some kind of a complex attractor so that it has chaotic behavior, typically your initial condition is going to place you on a point in state space that the system is never going to approach spontaneously. And in fact, the usual thing is for the system to as soon as you start the simulation, for it to zip away from wherever the heck you put it and converge toward whatever the complex attractor is or whatever the steady state is in the state space of this model. Well, you really don't want to have to wait around for that to happen, because sometimes the time constants, as you get closer and closer to these trajectories, to these stable trajectories, or you get closer and closer to a stable state, sometimes the time constants get real long because the driving forces are very small. And if you have a system with very small time driving forces, and very long time constants, it may take a very long time for that system to settle, to converge on a limit cycle or in the vicinity of a complex attractor. So what you want to do is you want to be able to start it out in that vicinity from the beginning. Okay? So you want to be able to identify that starting point and start the system close to where it's going to be operating anyway. And the final custom initialization, typical custom initialization, is to adjust parameters so that some particular condition is met, like maybe some particular intracellular calcium concentration is present in the steady state, or that maybe membrane potential is uniform everywhere in the steady state initially, or maybe just that the model has settled with non-uniform membrane potential, but membrane potential everywhere has settled down. So it may be maybe things are slightly depolarized in the apical tree, and more so as you get further from the soma. And you want the model to reach that steady state distribution of non-uniform membrane potentials. And so how do you adjust your parameters to meet a condition or to get to a defined starting point on a trajectory or to reach the steady state? Well, one way would have been to use a custom init procedure that is, and the init procedure is actually defined in the standard run library. But if you load your own custom init procedure last, then the standard library won't overwrite it. And this is what people were doing. They were writing code embedded in those custom init procedures. But now it's much better actually to use an f-initialize handler because it gives you much cleaner ability to keep track of what's your code and to avoid confounding yourself and producing code that's very hard for others to work with. So for example, come on, how do I get to the next page? Whoa. Ha! This is strange. I'm locked in this box and I can't get out. Zoom has locked me away. I can't get my cursor out of here. Let me see. Well, that's a big pain in the neck. That's really bad. Does anybody have any idea what I should do in such a circumstance? Robert?
What if he shares his screen and you switch back? Just Robert could share and then you return.
Can you? Yeah, can you share? Ah, good. I can stop my share and good. All right. Now I can share screen again. And I made the mistake of updating Zoom yesterday. It announced to me that the new version was available and I updated it. Seemed to be working so far. Okay, let's try. Let's take a look at an f-initialize handler. Okay, so how do we deal with f-initialize handlers? Well, an f-initialize handler, I think Robert's already mentioned, it basically is a class that we use to create something that will be executed at a particular time in the process of initialization. So the syntax is create your instance of your f-initialize handler class by calling h.f-initialize handler, and then in the parens you give the name of a callable, a Python callable, say procedure. All right? And that will give you a type 1 f-initialize handler, and those are the ones that are called right after the mechanism initial blocks are executed. And this is actually the best place to change state values. And for general purposes, it's the one you're going to be using most of the time. Okay? If you need some other type for some other reason, go read the documentation of the f-initialize handler class, especially about the different types. And then you'll be calling it with parens type, comma, pi callable. Okay? That's how you'll be declaring your f-initialized handler of types other than 1. All right, so let's see how we would initialize a cell to a steady state. Let's say I have a model. It doesn't have to be a model of a cell. It could have many, many cells in it. It could be a model of a network of several cells. It could have a lot of compartments, a lot of things going on. I want everything, and I know that if I wait long enough, if I run a simulation and wait long enough, I know everything settles down and there are no spiking cells. Okay? And all membrane potentials reach a steady point if I just wait long enough. Suppose I don't want to wait that long, or I don't want that wait to be obvious to others. Well, I could do what's called a initialization to steady state by jumping back in time. And my initialize handler procedure does this first. It sets time to some negative value, some large negative value. In this case, 10 to the minus third milliseconds. It's a, you might call it a back to the future initialization. The next thing it does is it checks to see if the model was expecting to use adaptive integration. If indeed it was, it turns off adaptive integration. Okay. All right. And that's what this is. At first, we check to see if we're using adaptive integration. And then after it discovers that, we turn it off and we set DT to a fixed value of our choosing, embedded up here as a built-in parameter. Okay. Then we do a continue run that starts at T0, that is way in the past, and runs for dur milliseconds, where I've defined dur to be, say, 100 milliseconds. And I'm assuming that 100 milliseconds is long enough runtime for this model to settle down. And after that, that means I have to know something about the dynamics of my model. I have to have tried this beforehand and verify that dur is long enough and that T0 is a big enough number to jump back into the past. After that settling down portion of the simulation, I can return to the present by assigning 0 to h.t. And if the simulation was supposed to be done with adaptive integration, which I check here, I reactivate CVODE, and then I reinitialize CVODE. And I'm ready to go. Okay. Oh, I'm ready to go, except for the fact that I need to initialize vector recording, which means that I will not have captured any of those simulation points at negative times. Okay. If I'm using a fixed time step, I call it a HF current just to make sure that all the currents are correct at times t equals 0 for all the local membrane potentials. Okay, so there's my entire F-initialize handler for initializing to steady state. And this is what I would use, say, if I had a cell that had different channel densities in different sections, and I wanted to let the cell have time to settle so that all compartments finally reach their steady state values. I'm not interested in forcing all compartments to have the same initial potential at t equals 0, nor am I forcing them to have the same resting potential. I'm allowing them to have non-uniform resting potential because there's evidence actually in the real world that real cells do have non-uniform resting potentials. And that, to some extent, that's a developmental thing that varies with, say, for example, whether chloride reversal potential is depolarized or hyperpolarized relative to rest. Okay, and here's how we would declare, how we would create an instance of an F-initialize handler that forced execution of SS init right at the beginning of a simulation. Okay. So if you look closely, you'll see this is the answer to one of the homework assignments for the day. Okay, what about initializing to a desired state? And this is useful particularly for chaotic models or oscillating models. And the rubric here is that you basically allow the just start the model running. Just let it run and give it enough time until it seems to be settling towards some attractor or some stable limit cycle. And once you figure it's close enough, then at the end of that warm-up simulation, you go ahead and you save the states. You create an instance of the save state class, and then you execute save state.save. And at that point, you've got a bunch of data in an internal structure in Neuron. And you could, if you want, you could save that data to a binary file, okay, by executing these statements. And then later in the future, if you recreated exactly the same model that you used to generate those saved states, well, in the future, you recreate that model, and then you execute this code, which creates an instance of the save state class, retrieves the states from the states.dat file, where you'd saved them before, and then you can use an finitialize handler to restore the saved states. Okay, and the finitialize handler, to do that, here's an example. This is the procedure it's going to call, and I'm calling it restate, which basically means it calls save state restore, sets t back to 0, reinitializes the adaptive integrator if it is necessary to do so. Otherwise, make sure that all the currents are appropriate for the local membrane potential at t equals 0, and then initializes vector recording. So this is the procedure that we want to have called during initialization that will restore states that were saved before. And this is the finitialize handler that we create to do that. Again, it's a class 1 finitialize handler, so restate will be called at the beginning of the simulation at the appropriate point to restore the states to what we had saved previously. Okay. The final custom initialization I'm going to mention today is initializing to a particular resting potential. And this is the situation you may find yourself in if you just want to make sure that your cell does have uniform membrane potential everywhere. Or if you want to replicate some of the experiments that people can do in a wet lab. Here's a typical experiment in a wet lab. Somebody takes a cell, and let's say it's an electrically compact cell, and they've patch clamped it. And since it's electrically compact, they can control membrane potential everywhere pretty well. And they run some simulations, and then they change the extracellular fluid. They wash in a bath that has maybe less potassium, or maybe more potassium, or maybe less sodium or more sodium, or there's some other ionic component in the bath which is different. Now, if the cell has got ion channels in its membrane that are which are permeant to these ions, and these ions can go through the membrane, and you've changed the extracellular concentration, you're changing the driving force for charge entry of the cell. You're changing the reversal potentials of these various associated with the various ion channels. You're going to be changing its resting potential. Well, what would an experimentalist do about that? Well, an experimentalist would say, look, I've just been experimenting on this cell and that's been sitting at a particular resting potential. So all of its gates are in a particular state appropriate for that resting potential. I did some measurements. Now I've changed the bath, and I see that the cell wants to shift to a different resting potential. I could let it do that, but what's wrong with that? If I let it do that, all of the voltage gated channels will change their gating state. So I'm not going to be operating on the same model exactly in the same exact condition it was before I changed the bath. I will be operating on a model in which not only did I change the bath, but I've also allowed the gating states of the voltage gated ion channels to change. So if I do an experiment and I see a different result, I won't know how much of that result is attributable directly to the change of the ionic concentrations, and how much of that result is attributable to the indirect effect of the membrane potential shift on channel gating. I will have a confound. The psychologists call this a confound. When you have multiple things going on, that can interact and contribute to an observed effect. You want to eliminate confounds as much as possible. Well, how can we eliminate the confound of the shift of membrane potential that occurs when we change the bathing solution? Well, one way we can do that is we can do something to counteract that shift. We know that when the cell is normally at rest, normally at VNet, then there should be a net membrane current of 0 in all compartments. If VNet is the resting potential of our model cell, and it's it's the resting potential everywhere in our model cell, then the net transmembrane current, net ionic transmembrane current in every compartment needs to be 0, doesn't it? At VNet. So what do? How do we go about this? What we do is, the first thing we do is we call a HF initialized with an argument of whatever the value of VNet is. If VNet was specified, say, with a Python variable called VNet, I would obviously drop the H dot part here. But this basically sets all local membranes to VNet, okay? And then make sure that all the voltage-gated channels are consistent with having sat at VNet for infinite time. So all the gating channels are in their appropriate status for the cell to have a resting potential of VNet. Now what we have to do is we have to march through the cell compartment by compartment and make sure that current balance of all the transmembrane ionic currents turns out to be 0. The sum of all transmembrane ionic currents must be 0. And the way to do it is to iterate over all of the segments of all the sections. And in this case, I'm just saying we have a single section model, so I'm just going to iterate over all the segs in SOMA. And you know exactly what to do if there's multiple sections. You iterate over for all sections in the model, then for the seg in all these sections. What I'm doing is I'm checking to see what I need to do to my ionic equilibrium potential for the leak. And the calculation is here. I add these things up, and then I divide that by the leak conductance in the segment, and that becomes what the leak reversal potential should be in that segment. Okay? It's really simple algebra to figure this out. Okay, to derive that, I leave that as an exercise to the reader. Okay? And I also leave as an exercise to the reader the problem of convincing any experimentalist that this actually produces a useful result. Okay? Because not only does it require a little bit of algebra that involves a lot of letters and dots and stuff, so it looks confusing, but also because the resulting leak equilibrium potentials will look very non-physiological. Okay? They can be all over the map. Some might be very depolarized looking, some very hyperpolarized looking, but the net result is that in every compartment when membrane potential equals VNet, the net ionic membrane current is going to be 0. Okay? So, I mean, it works. You'll see this strategy used in models that Michele Migliori has published. It works just fine. Okay. Again, I leave it as an exercise to the reader to derive this for a model that involves HH, and then convince yourself and convince everybody else in your lab that it actually worked out properly. For those of us who would prefer a path of less resistance, there's a different approach, which is, since we are the ultimate, gods of the channels that are in our cell models, in our models, we can invent a constant current mechanism that delivers a constant current. And we can use it to counteract all the other currents. So here is the N-model source code for a density mechanism that does one thing. The one thing it does is it delivers a current whose value we can specify. The current is a range variable, and the parameter that says how big the current is also a range variable. So it can have different values in different compartments. Okay? This is real simple, and it works, and it costs essentially nothing computationally because it's not solving any differential equations. It's just an algebraic statement. Okay, so in every compartment in your model, then you have to set the value of this IC parameter. Well, gee, that sounds difficult. How do we do that? Well, here's how you do it. Here's the procedure that marches through, in this case, I'm talking about a soma, but if you had multiple sections, you'd iterate over each section, and then you'd iterate over every segment in that section. So what it's doing is, in every segment of our model, it adds up all of the ionic currents. And how do we know those ionic currents have the proper value, have the value that they should have when V is at V init? We know that because we've called HF initialize. And remember that the type 1 F initialize handler is executed after, okay, after all the gating states are set correctly for whatever your local membrane potential is. So that means that each of these currents, each of these membrane currents in our compartment will have the values that they should have if the cell is resting at V equals V init. So we add them all up, all these currents, and we say, okay, we set our constant mechanism's current parameter to -1 times that. That's all it takes. Oh, we have to have inserted constant into the section that we want to affect like that. And if our model has different ion channels in different compartments, what we would probably want to do is create subsets, so that if some sections have other currents as well, then when it comes time to calculate the sum of all the ionic currents in those particular sections, we will include the appropriate terms for them. Okay? So if there was a calcium current, then we would include a term, what would be called seg.ica into our addition. Okay? And if we had other things going on in the segments, we'd have to add those in as well. But this is pretty good because this takes care of all sections that, of all mechanisms that write a sodium current. And this current, this seg.ik, is the total potassium current from all mechanisms that generated potassium currents, whether they're density mechanisms or point processes. So depending on how your N-model code is written, it could be very easy to extend this to handle very complex models with lots of inhomogeneity in their membrane properties. You just have to remember to iterate over the different section lists or subsets of sections. Okay? And that will do the job. And your model will, presto, start at the desired initial potential, and it will work fine, and even experimentalists will be able to understand what you're doing. You're doing what they would love to do. What they'd like to be able to do is get a patch electrode attached all over their cells so that they can in fact inject whatever currents they wanted to in every last one of these to force local membrane potential to whatever the value is supposed to be for whatever experiment they have in mind. They can't do it, but we can. Okay. So for the homework, what I'd like you to do is I'd like you to make a ball and stick model with these parameters. A soma 10 by 10 microns, which has Hodgkin-Huxley standard Hodgkin-Huxley channels, and a dendrite that's 1 micron long, 1 micron diameter, 500 microns long, and it has the pass mechanism with a specific conductance of 1/10,000th of a Siemens, that should be a uppercase S, per square centimeter, and a reversal potential of minus 70 millivolts. Okay, now DEND is going to be connected to the soma, and we know that DEND is going to want to rest at minus 70 because it's got pass, which likes to sit at minus 70, but we know that soma wants to sit at minus 65. So we're going to have a model that is going to have, in the steady state, very inhomogeneous resting potential. So guess what your task is? Well, the first thing you do is you're going to set up a space plot of membrane potential from one end of the soma to the opposite end of DEND. And you're going to zoom into that. You'll do a view equals plot on that space plot at the end of a 20 millisecond simulation to see what happens to V. Actually, you may have to change the Y value, the Y-axis upper and lower limits slightly to see how that evolves in time, because it's going to start out at minus 65 millivolts, and then everything is going to sag in a negative direction. The dendrite, the distal dendrite, more than the proximal dendrite, and that more than the soma. So what I want you to do is, having built that, I want you to add an f-initialize handler and associated code that will initialize the model to steady state. That doesn't mean force it to be minus 65. It means let it initialize to steady state. And the hint is it's going to use the Back to the Future style of initialization. Okay? For extra credit, start with the same model cell and add code that initializes the model to a uniform resting potential of minus 65 millivolts. In other words, that forces the resting potential to be minus 65. Now, you and I and everybody else in the room knows that we could easily do that simply by changing pass E to minus 65 in the first place, but that's cheating. So go ahead and do that. Okay? And that's all I have to say about this. Are there any questions? I'll make the slides available. Have we talked at all about the linear circuit mechanism? Is anybody interested? Go ahead.
Oh, I was just going to say, I think we mentioned it exists.
We mentioned it exists. Yeah, okay. Is anybody interested in the linear circuit mechanism? Anybody interested in instrumentation artifacts? Ah, Ben, thank you. That's good. I don't have to actually prearrange for planted questions in our group because fortunately there are some people who are interested in some of these things. All right, so why don't we talk a little bit about the linear circuit builder? Yes, indeed, Padma, definitely. We will do this next. Let me see if I actually have some, I do have some slides. The linear circuit builder. And what I'm going to do is zip through these a little bit, and we may get to the point where I just start Neuron and start using it. Basically, the linear circuit builder is a graphical interface tool that you can use to build models that contain linear circuit elements, by which I mean what exactly? Resistors, capacitors, and operational amplifiers, highly idealized operational amplifiers. That is linear over an infinite range of input and output values, and with infinite gain bandwidth product. Obviously, no such thing exists in the real world. Also, inductors are in there as well, and there's ground, there's currents and voltage sources, and we can do all kinds of things with the linear circuit builder, and including build circuitry that involves neurons. So, for example, we can then do experiments that allow us to explore how compensation of electrode resistance and capacitance might improve your recordings, or how not compensating for those things might degrade the quality of your recording. We can also implement things like gap junctions, including linear and nonlinear gap junctions. There's a tutorial about using the linear circuit builder on Neuron's website. On its documentation page, there's a link to that. But we're going to breeze through that quickly. So at this point, perhaps I can simply resort to using the tool. And let me just do edit preferences and go for a larger select. Okay. Okay, close. So I'm just going to start, I'm just going to be, well, Python. All right. So now I've got the Neuron main menu panel. I could have just run NRN GUI and got it the same, but I'm being orthodox here. So build linear circuit. Okay. Now this isn't a very prepossessing looking thing. It's got 4 buttons, and we're going to use them in the order from top down: arrange, label, parameters, and simulate. It's got this set of stuff over on the left side. I don't know how well you see it on my screen, but these are a wire icon, a resistor icon, a capacitor icon, a squiggly thing that's supposed to be an inductor, a thing that's supposed to be a battery or voltage source, a line with an arrow next to it which is supposed to be a current source, a ground, an operational amplifier, and a couple of different electrode thingies that are attached to what looks like a stick figure of a model cell. And let's use this to build a model something or other. And the something or other we're going to build right now, whoops, is going to be a very simple RC circuit. Okay? So on the arrange page of the linear circuit builder, or when the linear circuit builder is in arrange mode, ARRANGE, we can drag stuff onto the canvas here, and we can make as many instances of whatever it is we're interested in as we like. And if we have some we don't need, we can get rid of them by I click on it and drag it off. And I click on it and drag it off the canvas. And I click on this one and get rid of it by dragging it off the canvas. And at the end of today's session, I'll have to pick up my laptop computer and dust all the little grounds off of the desktop. But for now, I'm going to make a classical RC circuit. I'm going to start with a capacitor. And as you'll notice, as I click on one of these things and drag it onto the canvas, you notice it comes with these little red things. These are connections, connection points, and it comes with an automatically generated name. The leading character tells you what kind of a thing it is, and the number is an index, which is meaningless, but it's just automatically generated so that we don't run into a collision in namespace. Okay, so this is going to be a capacitor, and I'm going to draw my capacitor like that, vertically. And you'll notice that if you click on one of these little red terminals, you get this rubber band-like effect. The other terminal stays put. Okay, And if you want to move something bodily, you sort of click in the middle of it, and then you can drag it around, okay? All right, so there's a capacitor, and I want to connect a resistor to it. So I'm going to click on the resistor thingy, and holding down my mouse button, I drag my resistor over to here, and whoa, what was that? When I brought it close, when I brought the one red circle close to the other one, it made a connection. And that little square box signifies a connection between two terminals of two of these elements. These are circuit elements over here. This is actually a palette of circuit elements, and these are the instances of the circuit elements. So we now have a resistor and a capacitor hooked up to each other. Now, what if I want to have a voltage source? I click on the battery icon, and I bring this over here, and I'm going to rotate my battery so that it's like that. And now I see that I'd like to move the labels around. So I'm going to click on the label radio button, and I'm going to move the R5 label to there, and I'll move the C4 label to there. I'm going to move this B6 label to here so it looks nicer. Now as I look at this and I think, why do I want this to be called B6? Or why do I want that to be R5 and C4? Those numbers are simply artifacts of the sequence in which I created these things. I just want this to be called B. Or maybe I just want it to be called V. Who knows? But I want to change the labels. So I click on Change. And then I can click on a label. And I can change the device name by clicking in that Edit field. Keep my mouse cursor there. And a backspace. So it's just called C now. And I can change the name of this device from R5 to R. Click on Accept. And I can change the name of that device from B6 to B. Now I could have followed Bill Gates's example and called it ham sandwich if I like, but I want these to be meaningful names that are suggestive to electrical engineers. Now I want to complete my circuit, which means I need to arrange things. I need to continue arranging. Click on the Arrange button. What do I need to do? I need to connect my battery to my resistor. I'm going to do that with this device, which is a wire. Okay, and there one end of the wire is connected to the resistor. The other end of the wire is here, and it's connected to the battery. Finally, I don't have a circuit completed yet because these two things are not connected. So I'll connect the one to the other with a wire, and then I will ground the circuit. So that means that all the nodes down here, all these connection points down at the bottom, are connected to ground. They will be isopotential with ground. Now all those little dots in there don't mean anything bad. It is really a wire. Well, actually, it's not really a wire, but it's meant to suggest a wire. Okay? So now I have a battery connected to a resistor and a capacitor. I want to see the voltage at this point and the voltage at that point. So I want to create names for the potentials at these 2 points. Okay, I click on Change, the Change button on the label page now, Change, and I click on a node, and it allows me to give the voltage at that node a name that I can use to refer to the voltage at that point. I'm going to call it Vin. Okay? And I notice that in its usual helpful fashion, it's not exactly where I want it, but I'll move it later. I want to call this voltage here at the junction of the resistor and capacitor V out. So I click in that field and I type VOUT, and there we go. And now I will move the labels to where I like them to be. And you'll notice as I click on a label, the thing that it refers to is highlighted in red. So there's never any reason to be uncertain about what's in your circuit. There's my resistor. There's my capacitor. Okay. There's my battery, all set. We're all set to go. We now have a circuit. Parameters. We have names for these things, but we haven't said what their values are. We haven't said what the value of R is. We haven't said what the value of C is. What is the value of R? Parameters. Let's let that be, for right now, let's leave that alone as 1 nanofarad, 1 megohm for R and 1 nanofarad for C. Okay. We'll just leave them alone. We'll change them later, maybe. Now, what about the voltage that this battery is going to provide? Well, a battery is a voltage source, just like a current source is a source of current, and it is a signal source. So if we click on this button here, source F of t, it'll list all of the source elements, and the only one here is the B, the battery. And I can scroll down and select it. Come on. Oh, there we go. Eventually I got the B panel to appear. And what does it say? It says, well, I could select this, I could click on this, and then it would ask me, basically, it would give me the opportunity to play a value, to vector play a value into some variable. But no, I'm going to say I want to set the durations and the amplitudes. This is like the single electrode clamp. So there's an initial period called 0, another epoch called 1, and a final epoch called 2. So this is during this first epoch, which is not going to be 10 to the 9th milliseconds. I'm just going to let that be 1 millisecond. The battery supplies 0 volts. During the next 1 millisecond, the battery will supply a voltage of 1 millivolt. And during the final episode, which I'm going to allow to be infinitely long, it will supply 0 millivolts. So this is going to be our typical, our classical rectangular pulse of voltage, okay? Just like a standard, you know, three-phase current voltage clamp experiment. All right, so we've taken care of our parameters for our battery and for our other circuit elements. And we're ready to run a simulation. If I click on the simulate button, I'll drag this down here. That's the circuit parameters themselves. If I now click on the simulate button, I have the opportunity to specify what the initial conditions are. If I look here, I see only one energy storage element. That's the capacitor. There's no inductors, so there's no other storage elements, and there's no other capacitors. So this is the only energy storage element, and I have to say, what is the voltage across the capacitor at t equals 0? So I click on initial conditions. Let me drag this down. I get to say initially the voltage at the V out terminal is 0, and the voltage at the V in terminal is also 0. So it looks like I get to say what the initial conditions are for each of the voltage nodes, not just what's stored in the energy storage elements. Okay. And it says here that unnamed nodes get a value of 0 automatically, and cell nodes are set to the value of V init. Okay, well, that's good. So much for that. We don't have a cell. We have this RC network. All right. We can see things that we might want to graph. I'm going to skip over this state. Well, let me just click the states button. Oh, look at that. The states in this model are the voltages at our 2 voltage nodes and the current delivered by the battery. Okay, that's good to know. These are the things that Neuron is going to be solving for when it runs a simulation using this circuit. Okay, so Neuron is going to calculate the current delivered by the battery, and it's going to calculate the values for V out and V in. Good to know. We want to have a graph. So I click on this new graph button. This graph is going to be different from the graphs that we would get with the Neuron main menu panel. So this is here, and it doesn't have the same appearance as our usual graphs does, but it allows me to select from a pre-selected menu, specifically the states. So I can plot V in, and I can plot V out. And I think I'm going to create a different graph. And use that to plot the battery's current. Okay. So there we are. These are our graphs. Now, before we do anything else, think of what is it that this is going to show. What is the voltage V in going to look like, and what is the voltage V out going to look like? Anybody have an idea? I'm not seeing hands because I don't have that set up yet. Let me see if I can see participants. Participants, there we go. Yes, I see a name. I see somebody's unmuted. What would you think is going to happen?
V in should be a step the way you defined it.
Good.
The 3 levels.
Right, good. And what will happen to V out? Well, I'll give you, yeah, go ahead.
Charge up. It should charge up. Exponentially.
It will asymptotically approach some value, yes. What value will it approach? It'll approach the value that the battery is applying, right?
Yes, with the time constant defined by RC.
Right. And then what happens when the battery voltage drops down to 0?
It'll be exponential decay, but just with the opposite concavity.
Yep, exactly. So on the way up, it's going to be concave down, and on the way down, it'll be concave up. And it'll be continuous. It's never, V out is not going to jump abruptly. V in will jump abruptly, but we know that that's just a fiction, because memory electrical potential nowhere changes instantaneously. And we can talk about why that is sometime if you like. But in any case, let's see what actually happens. Do these predictions actually work? Does this actually turn out to be the case? So I need something to make a simulation happen. Tools. I'm going to take a run control panel, even though it's got a lot more power than I really need for this purpose, because it allows me to advance and stop and fiddle with stuff. So if I just run a simulation, I should have asked you guys to predict the shape of current. Some of you probably knew and are bashful and wouldn't have said. So let's take a look at this. Let me actually use the color brush to make these things a little more readily seen. So V in is a heavy red line and V out is a heavy blue line here. And I'll go back to crosshair. And the current is going to be, I'll let that be a heavy red line. crosshair. Okay. All right. So you're absolutely right. It looks like this is concave down. And if I had any doubts about that, I could simply change the battery's parameter that controls the duration of the voltage pulse. I could make that voltage pulse say, whoops, I don't want that. I want 2 milliseconds. Let it be 2 milliseconds. And now let me run another simulation. Okay, now we see the concavity and the convexity. The concavity is down, and here the concavity is up. Okay, and yes, it does asymptotically approach the Vn value. Does everybody know why the current does this? Can anybody explain why the current does this?
I think it would be because the voltage across the capacitor is countering the potential of the battery.
Yeah, yeah, exactly. When the battery's voltage first jumps from 0 to 1, the voltage at the battery end of the resistor is 1, but the voltage at the capacitor end of the resistor is still 0. So there's a big voltage drop across the resistor, and we know that voltage drives current. So that means there's going to be a big current through the resistor. And so that current is equal to the battery's voltage divided by the resistance. So 1 volt divided by 1 ohm, and you get 1 amp, or 1 millivolt divided by 1 megohm gives us 1 nanoamp. And as the capacitor charges, the value of V out becomes more and more positive, starts to approach the value of V in, so the driving force for current flow through the resistor gets smaller and smaller. Exactly this exponentially decreasing current. Now when the battery voltage falls back to 0, at that point, our capacitor has charged up and has, it looks like about 0.8 millivolts or so here. Let me just see. Yeah, about 0.86 millivolts. So there's 0.86 millivolts at this end of the resistor and 0 at this end. So the current is going to immediately jump and follow in the opposite direction, go back in the opposite direction. That's why it drops from this slightly positive value to a negative value. And the magnitude of this jump is what? It's exactly 1 nanoamp. Why is that? Furthermore, if I changed Dürer, well, come on. My mistake in using the spinner. I should not have used the spinner. Let me just change that to 1 millisecond. If I run another simulation, that's a millivolt. And what's the magnitude of this jump? From here to here, that's a millivolt also. Why? 0.372 to minus 0.612. Is that right? Well, it should be a millivolt. Close to. What happens if I make it a tenth? And run another simulation. How big is the jump? What is that value? I can't even see it. Oh, well, that's a question for you. There's a tutorial on using linear circuit builder on the website. Let me make sure that it's still there. And I commend it to your attention. because you can then use it. You can use this linear circuit builder Well, there should be a linear circuit builder tutorial there. Darn it. There isn't one. Well, I'll just have to make one up now. But in any case, there are ways to use it with model cells.
Sorry, Ted?
Yes.
I think, but do not know for sure, that if you go into the exercises from the previous courses, there's a linear circuit builder there.
You know, I bet you're right about that.
So that's under
Let's do that.
documentation on the website.
That's exactly right. Let's go to the documentation. Actually, I could have.
And then the neuron course exercises.
Yeah, documentation. Oh, courses. Well, just go to documentation.
Second from the bottom on your screen right now. Down.
Neuron course exercises. There we go. Neuron course exercises. And well, let's take a look and see. Introduction to the GUI, morphometric data, scripting, using NModel. Oh, yeah, look at that.
Okay, so we should make it available.
It's a placeholder. Okay, so we should make it available. My error. But there's a way to do it. And I can show you very quickly exactly how, if you have the time. So it'll probably take less than 5 minutes. I'll do this for the benefit of those who have the time to stick around for it, okay? So, okay, there's our favorite from Neuron Import HGUI. And let me say soma equals H section, name equals soma, soma diam equals 10, soma L equals 10 divided by H pi. There we go. Now we have a model cell that has a surface area of 100 square microns. Soma, we say H dot HH insert soma. There we go. So now our soma has Hodgkin-Huxley channels, and we could do an experiment on it. We could inject current into it. But now that we do have a model cell, we can actually do that experiment using instrumentation that we build ourselves using a linear circuit builder. So here's our favorite linear circuit builder. I'm going to create an instance of a model cell. Actually, it's not an instance of a model cell. What it is it's a widget that allows us to access the node at the middle of the default section. And we could change that if we want, but I'm not going to change that now because there's only one section and there's only one node in it. I'm going to move this label so it's, well, maybe I can move it, maybe I can't. It doesn't seem like I can move it. Let me not do anything else for fear that I might break something. Okay, so let me move this model a little further over. And let's say I want to attach a voltage. Well, let me attach a current clamp to it. I want to make this thing fire a spike by attaching a current clamp to it. And my current clamp, however, is not going to connect directly to the cell, but instead will attach through an electrode, a glass microelectrode. And my glass microelectrode is going to have some interesting properties. And let me just show you the equivalent circuit for my microelectrode. It's going to have an access resistance that sits between the current source and our cell. And there's our current source. And I'm going to move this down here like this, and I will attach a ground. Okay. And it's also going to have a capacitance. I see I might want to use some different positioning just to make things more readable. Okay. There's going to be some stray capacitance in our glass microelectrode. And I'm going to ground this point. So what's this business up here? This is an equivalent T circuit for the electrical properties of a glass microelectrode. This resistor, which is split in two, represents the resistance of the electrolyte that fills the electrode and whatever access resistance there is at the pore in the side of the cell where I have attached my electrode, and the capacitance of the electrode. So let me change some labels and move some labels. Okay. And I'm going to change R4 to R1. I'm going to call R1. I'm going to call this R2. All right. I'm just going to call this C. That's the capacitance of the electrode. Or I could call it CEL or CE. Okay. Now, I need to know, I'm going to want to know what is the actual membrane potential of the cell. So I need to label this node, and I also want to know what is the observed membrane potential of the cell, because I can't observe the real membrane potential. I can't actually physically record from that point without using this clunky glass electrode that sits between me and the cell. So I can only observe the membrane potential at one of these two nodes here. Okay, so I'm going to label this node to V observed. Okay, or I could call it V rec or something like that. This is what we see. This is what the experimentalist sees. And this is VM. Okay, the actual membrane potential of the cell. Okay, let me go to parameters. What do I want to use as my resistors and capacitors? Well, let's use values that are drawn from practical experience. And I can tell you right now that if you have a microelectrode, if you have a patch electrode with a resistance of 10 megohms, you're doing real well. So we're going to say that our microelectrode has a resistance of 10 megohms, and it's divided into two resistors of equal size. And we're going to say that the electrode's capacitance is a couple of nanofarads. Now, what's a nanofarad? That's 1,000th of a microfarad, right? We'll see. We'll see what happens with our simulation. And let's just actually set up the source. What are we going to do with our model cell? Is we're going to stimulate it. We're going to stimulate it with a current pulse that starts at t equals 1 millisecond. And, excuse me. And let's see, the initial membrane potential is minus 65. We want our cell to start out at rest. And we want the stimulus pulse Oh, no, nanoamps,
Pardon?
0 nanoamps. Sorry, 0 nanoamps. And we want our duration of our current pulse to be, say, 1 millisecond. Try that for the heck of it. And we'll just see how big it needs to be. Let's say 0.01 nanoamps. And duration, the last duration is infinitely long. Okay, so now we have our stimulus, and what we can do is we can then start to plot things. So I can go to the simulate page. I need to do initial conditions. Whoops. What is the initial condition? We'll see that Vrec is equal to the resting potential of the cell, minus 65. If I didn't say that, then there'd be a problem, because this capacitor would start out at 0 millivolts, which is highly depolarized, and it would blast our cell with a big depolarizing current, or maybe a tiny depolarizing current, but who needs that? We don't need artifacts at the beginning of our simulation. Okay, so we've got that set up, and now I want to do my graphs. New graph, and what is it I want to plot? On one of them, I want to plot I5, which is the current generated by our current clamp. And I want to also plot the recorded potential and the actual membrane potential. Okay, so let me move things around a little bit more. And let's see what actually happens. Let me get a run control panel. And let me do an init and run. Is this going to explode? Let's see. Whoa! Oh, look at the crazy axes we're using here. This is not what we want. 0 to 1 millivolt in both directions. No, we want to have something more like what a real voltage axis graph would use. So we're going to have the x size be 0 to 5. That's fine. And the y size is going to go from minus 80 to plus 40. Okay. So this is odd. Why is it that, oh, you know what I did? I have not controlled the voltage at that point after all. Oh, that isn't so good. That's what's actually happening. Our capacitor is starting out at 0 millivolts. I'm only controlling the voltage there. And that doesn't mean I've stored any charge on our capacitor. So what this tells me is we need to go back to our label page, and I hope I can label this point. Can I label this point? This is going to be called, I'll call it VC, or maybe VX, because we never actually can observe it. But now VX is the value of the potential at that node. And that's going to allow us to control the charge on that capacitor, so that capacitor will not be sitting at 0 millivolts ready to blast our cell in the depolarizing direction. Ta-da! I did what I said I wasn't going to do, and sure enough. So let's go to the simulate page and go to initial conditions. And now we see that we have control over Vx, and I can make that be minus 65. So now we shouldn't see that crazy artifact occur. If I do a init and run, aha, what is the value of the source? 0.001 nanoamps. 0.01 nanoamps. Okay, so that's too small, maybe, to do anything useful. Let's try that. And let me do an init and run. Okay, so now we see some current is depolarizing the cell a little bit. Let me try 1 nanoamp. Do an init and run. About 10. About init and run. Now that's interesting. I'm not getting a spike yet, am I? I am not getting much charging in my cell either. Look at this color brush. That's the voltage. I should say that's the voltage that we can observe. And here's what's actually going on in the cell with a little blue trace. So there's a huge electrode artifact. Our electrode is keeping us from delivering current to our from getting current to our cell very easily, and it's producing a big electrode artifact. So maybe what I need to do is to provide. Now wait a second. The current can only go two places. It can only go into the capacitor and to the membrane. So let me make that amplitude bigger, which is seeming a little excess. And this doesn't look at all like what we expected. So I think we have a situation where we might want to reduce our duration of the current and run another simulation. And I'm still really not getting much of a of anything out of this. What's going on? Is our capacitor loading down our cell? Let me make it be 0.1. Let me try this. I think maybe our capacitor was loading down our cell. Our capacitor was so big that it was acting as a huge capacitive load on our cell, and we couldn't get our cell to fire a spike, and we also had trouble charging it. Do an init and run. Make the amplitude maybe a little bigger. And now we're starting to get what looks like a spike. Not a very strong one, but maybe the capacitor is still too big. Make it smaller. Init and run. Look at that. Let's cut the amplitude back down to 10. Do an init and run. Cut it down to 1. And do an init and run. Okay, and now what if I let it run for longer? It's looking like it's trying to make a spike. Okay, so we're seeing, make that a little bigger. There we go. Finally, we've got a spike. And let's take a look at this at a shorter time scale. Okay, and you see there is a artifact in the electrode, and we see our cell is not making a very healthy looking spike. And the reason it's not making a very healthy looking spike is because of this electrode capacitance. If I make that 10 times smaller, we get our spike becomes much bigger, it's easier to get. And it has what's looking like a better time course. And I can cut this amplitude by half, and I bet it'll look even better. So you can see the effect of electrode capacitance on the cell pretty dramatically. You can see how electrode capacitance can just ruin your ability to stimulate and record from a cell. Okay? So these are the kinds of things you can do by playing around with the linear circuit builder. You can learn a lot about the interaction between your instrumentation and your model cell. And so it gives me an appreciation, a greater appreciation than I had for the importance of electrode capacitance. Now, for those of us who are electrical engineers, we realize that 1/1000th of a nanofarad is simply a picofarad, and a picofarad is actually not that small for certain purposes. And it's no surprise that something on the order of 10 or 100 picofarads could load down a signal source as delicate and small as a model cell with its Hodgkin-Huxley currents. Okay, so that's about all I have to show for this, and I thank you for your attention. Are there any questions now? All right, great. Well, we'll cobble up a tutorial appropriate for use with the linear circuit builder and make it available. But in the meantime, you've seen it here, and you've seen a bit about how to work with it and how to debug what's going wrong when things seem to be going wrong. And with that, I'd like to thank you again for attending the course and for your questions and participation. Robert?
Just second that. Thanks so much, everybody, and all the best. Feel free to contact us if you have questions or comments.
Thanks a lot for providing these lectures.
Well, we're glad you appreciate it. And the feedback we get and the interest we get helps us guide the development of Neuron to make it easier to use and figure out what things it needs to be able to do next. Alrighty, bye-bye all.